This is the Section 7.5 notes for the online trig class, a unit circle approach to trigonometric functions. We're going to be looking at the unit circle and how it relates to trigonometry and how it's a very crucial part of understanding sine and cosine and tangent ratios for special angles. So a unit circle is a circle whose radius is 1 and whose center is at the origin. So notice it's on the xy axis and we have this center at the origin. On the unit circle, we'll let theta be any angle that's in standard position. So remember that's centered at the origin. And we have the x-axis right here is our initial side. And there will be some point on the circle that we'll stop at for our terminal side. So that point will be an x and a y. Since theta can be any angle, the point P can be found for some basic angles. So for example, the quadrantal angles, are the ones that occur at, remember, the x and y axes. So this would be the points 1, 0. This is 0, 1, just the ordered pairs. This is 0, negative 1, and this is negative, excuse me, I wrote that backwards. This is negative 1, 0, and then this is 0, negative 1. So 180 degrees is over here, so that means that point is the negative 1, 0. 270 is down here in the third one, because remember it's 90, 180, 270. So that is 0, negative 1. For the point, because they're only asking for the point here, 90 degrees is the ordered pair 0, 1. 360 is back over here at 0, so that would be 1, 0. And that's also the same location as 0 degrees. Negative 90 means you go 90 degrees clockwise, because remember counterclockwise is positive and clockwise is negative when we measure our angles. So 90 would be down here if we go in the negative direction. So that would be 0, negative 1. Trigonometry gives us words like sine and cosine to describe the relationship between the angle and the point on the circle. You need to keep in mind that any variable, in this case t, can be used to denote the angle. So if we let t be a real number instead of saying that it's just theta, and we'll let p be xy, a point on the circle that is a unit circle. Very key thing here is that r is equal to 1, so that means this is 1. So anytime you form a triangle here, your hypotenuse would always be 1. So remember, sine function is y over y over r. So that would be this y value, whatever that height is, over 1. So when you're dealing with the sine function associates an angle t with a vertical coordinate, which is the y coordinate, of p, and is denoted sine of any real number equals y. The cosine function, which remember is x over r, that's adjacent over the radius, which is the hypotenuse, associates each angle t with the horizontal coordinate or the x-coordinate. So what we get here is that anytime you're dealing with a point on a circle, a unit circle specifically, the cosine value of the angle you're considering is x, the y value is the sine of that same value. So that's going to help us come up with a lot of different relationships. So we can use a calculator. So let me pull mine up. When you're using your calculator, you'll want to make sure that you're in either degrees or radians correctly. So I'm going to do all the degree questions first, and then I'll go through and do the radians. So sine of 180. Now in my calculator, I have to enter in the degree or the angle measure first. Some calculators you enter in sine first. So that is 0. Oops. It's trying to skip. So sine of 180 is 0. Cosine of 270 is another one that has degree measures on it. That is 0. Sine of 360 is 0. Sine of 90, it should be 1. So let's see, cosine of 90 I also have, which would be 0. And cosine of negative 90, which is 0. And then we also have cosine or sine of 0 degrees. Notice this one's not in degrees. Anytime it's just 0 without a degree symbol, it's actually radians. So sine of 0 degrees is 0. Now you're thinking there's a lot of zeros up here. How do I know this is doing the right thing? Well, 180, remember, is over here. And in your y value, because remember sine is attached to the y value, is 0 over here. 360 is on the other side of the x-axis, and so is 0. So the y value of those is 0. This is cosine for 270. Cosine is attached to the x value. And when you're down here, this is an x value of 0 and a y value of -1. So for cosine, that actually is 0. Cosine of 90, that would be straight up. That also has an x value of 0, because remember, cosine has to do with x. Sine of 90 relates to the y value of 90 degrees, which would be +1. So then we're going to go through and we're going to change this to radians. And we're going to find pi cosine, which is -1. We're going to find 2 pi as a cosine, which is 1. 3 pi divided by 2, but we're going to be doing sine of that, so 3 times pi divided by 2, and then we're going to do sine, which is -1. So you can do these without the calculator. We're just trying to show you that they are coming out to what we expect. Negative pi over 2, just jumping around a little bit, so pi divided by 2, answer is negative. And then we are doing sine, so that's -1, and then cosine of 0. Now I'm not going to use my calculator for this one. 0 radians is right here on the x-axis, so the cosine, remember, is the x value here. This ordered pair would be 1, 0, so this would be 1. So see, you don't have to use the calculator on the ones that will fall on these nice places. From the definitions above of the sine and cosine function, we can now define some more information about the other trig functions. So if t is a real number and p is x comma y, that's our point, on a unit circle, which means our radius is 1. If x does not equal 0, the tangent function associates the y coordinate to the x coordinate, so that means that tangent would just be y divided by x. Cosecant, remember, cosecant is the reciprocal of sine. So if you have 1 over sine t, since sine is related to y, this would be 1 over y. Secant, remember, is 1 over cosine, so this would be 1 over the cosine, which is represented by x. Cotangent is just the reversal of tangent, so that would be x over y. So now that we know these ratio relationships, we can find pretty much any 6 trig values if we know the ordered pair of the angle that that's associated with, especially if it's on a unit circle. Now, if your circle is bigger than that, if it's like a radius of 2 or 3, we'd have to consider that a little bit more deeply. It would change some of our answers. But for us, so far, we are dealing with only a unit circle at this point. So sine of t would just be the y value. Cosine of t would be the x value. Tangent's going to take a little bit of work because we have to put the y over the x. Notice we get something that looks like it needs to be cleared, so I'm going to multiply top and bottom by 5. And this is -2 square root of 6. Cosecant is the flip of this, so that would be 5 over 2 square root of 6. We need to get that square root of 6 to be rationalized out of the denominator. So that would be 2 times the square root of 36, which is 6. So 2 times 6 is 12. So that would be my cosecant. Just circle these as I get them. Secant's just flipping cosine, so that'd be -5 over 1, which is just -5. And for cotangent, we flip tangent, which means we do get a radical in the bottom, so we need to rationalize that. Remember, this ends up being square root of 36, so that's 2 times 6, which is 12. Be careful, do not try to reduce 6 and 12 here, because this is an inside number of a radical and this is an outside number. They are not the same. Okay, so far everything we've looked at has referred to the unit circle, and that meant its radius was 1. If we have a radius larger than 1, so for example, they've made up a circle a little bit bigger than the unit circle, so any generic radius bigger. What we note is that the two triangles that get formed, one from the unit circle and one from this larger circle, they share this angle and they both have a 90-degree angle, and they're going to end up being similar triangles. Similar triangles means that the ratio of y over y star compared to, say, x over x star should be the same. So what they do is they came up with this list of rules that said, okay, if we map the circle or the triangle from the unit circle, we should be able to map those ratios to any generic r. Because notice that all that's really happening here is anywhere there was a 1, that's turning into radius. So we've already defined these before. I always do it ahead of time because this is just too long to wait to start talking about this. But sine would be y over r, cosine is x over r, tangent is y over x. This would be cosecant, secant, and cotangent. And then there's another fact here. When you had the unit circle, x squared plus y squared equaled the hypotenuse 1 squared, so that was Pythagorean theorem. Now we have Pythagorean theorem where the radius is not 1, so it's now r squared. So for an angle theta in standard position, let P equal xy be the point on the terminal side of theta that is also on the circle x squared plus y squared equals r squared. And we're just going to re-summarize these things. So sine theta is y over x, or sorry, it does not want to let me erase. It's y over r. Cosine is x over r. Tangent is y over x. Notice because x cannot equal 0. Remember, that's a standard. When you have a variable, your radius can't be 0 anyways. But when you have a variable in the denominator, you don't want it to be 0. We flip it for this, so r over y, x over r. Oh, I did that again. I will apologize. I do have a head cold. Speaking and writing at the same time has become a little difficult. So x over y. All right, finding the exact value of the 6 trig functions now that we know these ratios. So if we have an angle theta and we know that we have a point 3, negative 4, so 1, 2, 3, down 1, 2, 3, 4. Here's my point. That means that can be turned into a triangle. Notice that it has positive 3 and negative 4 as the x and the y. Those are the lengths of those sides. We would need the hypotenuse. This is probably not going to be a unit circle because usually the hypotenuse, remember, is larger than the other two sides. So 3 squared plus negative 4 squared equals what we call r squared. So this is 9 plus 16 equals r squared, which is 25 equals r squared. And if we take the square root, r equals 5. So now that we know our trig functions, using this ratio that we've come up with for all the different sides, we now have our x, we have our y, and we have our r. So sine is y over r, so that'd be negative 4 over 5. Cosine is x over r, so that would be 3 over 5. Tangent is y over x, so negative 4 over 3. Remember, the last 3 are all just flipped. So cosecant of theta would be negative 5 over 4. Secant of theta would be 5 over 3. And cotangent of theta would be negative 3/4. Earlier we found that when theta is an angle in standard position and our point P is on the unit circle, that sine theta was y. So notice this is divided by r, but r is 1. Cosine's x, tangent's y over x, cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. The reason this is important is because notice that in all of these after sine and cosine you get what are called domain restrictions. There's places where you could possibly divide by 0. That's why they have to have that little list written there. So now we're going to talk about the domain and range of the trig functions, and that's going to lead into the next section where we'll actually start talking about graphing trig functions soon over the next 2 sections. So find the domain and range means that we would look at, remember, domain as being an input and range is something to do with output. So sine theta, the input is the theta. We are saying here's a specific angle we've looked at. The output is the answer or ratio. So that would be y. That means that I can plug in any number I want for the angle. Because remember, we can use any number and just keep subtracting or adding 360 to figure out what that would be between 0 and 360. The range, though, is your unit circle. So your circle, if you're on the unit circle, you never get higher than 1 or more to the right than 1, and you never get more to the left or down more than -1. So all of the numbers you get for your x's and y's are going to fall between -1 and 1 because they're going to be ratios of numbers. I'm not going to justify those, but there's probably a video or something you can look at there, but this is just relating this to the unit circle. So for cosine theta, the input is still theta, the output this time is x. The domain is still going to be all reals. You can plug in any number you want as an angle, because remember we said even real numbers can be considered there. The range is still the unit circle ratio information, so that would be -1 to 1. For tangent theta, the input is any theta that does not produce division by 0. The output is going to be y over x. So what this means is that the domain we have has to be restricted. And the reason this happens is because anytime, remember, tangent is y over x. Anytime x equals 0, we would be in trouble. Well, where does x equal 0? X equals 0 at pi over 2 and down here at 3 pi over 2. Notice it does not have a problem when you're at 0 or at 2 pi over 2, which is pi. That's why they say that it has to be odd integer multiples of pi over 2. So essentially, anytime you're at the top up here or down here at the bottom, that's when you're going to have those things. A better way to think of that, I mean, like, you can't really write it any more clear, is that everything from negative pi over 2, because that's this guy down here, to pi over 2, anything between those is good. And you could keep going from here. You could say even pi over 2 to 3 pi over 2 is good. So you could keep listing those things forever, but the best way to say it without having to write all those lists, because it would go on forever, is that you would, because pretty much it's just you go between, here's the right side between two angles, here's the left side. As soon as you hit these, you get into trouble. So it's always just half of a semicircle all around. So that's what they're explaining there. But the range is any number, any real number. So when you do these ratios of y over x, any real number could pop out. For cotangent, the input is, the cotangent one, remember, is x over y. So you can't have a y equal to 0, which means that we get into trouble at any place that you're on the x-axis, because remember, this would be 1, 0, this would be -1, 0. So in both those scenarios, you get in trouble when you divide by 0. So the input is still a theta. The output is still going to be something related to the ratio x over y. But for the cotangent function, you have to stay in, how we want to say this, it's anytime you're between 0 to pi or pi to 2 pi, as long as you're not hitting those points where you're on the x-axis, you're fine. So if we want to stay kind of consistent with how they said that in the previous part, we could say it's anything except even, or not even even, it could just be integer multiples of the, so it's all, they don't really leave a lot of room to write this, all reals except integer multiples of pi. And the range again would be all real numbers. Cosecant, the input is theta, and theta cannot produce division by 0. The output is 1 over y. So that means the domain of the cosecant function is all the real numbers except integer multiples of pi, which is, remember, the 180 one. That's the one we just talked about with cotangent. And the range is all real numbers greater than 1 or less than or equal to -1. Now the best way I can show you that is actually, I'm going to go to a program called Desmos and show you. This is a free graphing tool. And we haven't got to the part where we're going to graph yet, but they kind of gloss over this in the textbook a little bit, explaining how they came up with their domains and ranges. So if you had, we were doing cosecant, so if you had sine of x is a function that looks like this. Notice all of those are kind of like ordered pairs that we have, and it's a nice wave. When you do cosecant of x, notice that these guys are going in the opposite direction. So notice how this is kind of going in a wave. At the peak of each of these, we get these parabola-like shapes that are our cosecants. So notice for the cosecants, they kind of reverse what's going on for the range. Whereas this was -1 to 1, now I have things bigger than 1 and I have things smaller than -1. So this is the easiest way, I think, to understand it, is to look at the graph. And the same thing happens with cosine of x, which we'll graph in one of the next sections, and secant of x. So notice you also get that relationship that while the cosine is a wave, the secant kind of goes in the opposite way. So the y values get bigger than 1 and less than -1. So that's what's going on there. So that means secant's going to operate, like I said, a little bit like that one. So secant, the input is any theta that does not produce division by 0. So I'm going to try to write that in. That does not produce division by 0. Because remember, secant is 1 over cosine, so that's 1 over x. So anytime x could possibly be 0, which would be at 90 degrees and at 270 degrees, that's when you're going to get trouble there, and you'll have a blank where that's, if you look back at the graph, notice that we have places where we don't have any graph that is blue. Those are kind of empty spaces, so that's why it's not continuous. The output is going to be the 1 over x. The domain of the secant function then would be, it's related to the tangent one, so it's the pi over 2 odd integer multiples. It's really hard to write this in here, of pi over 2. The reason for this is, remember, the other function that also divided by x was tangent. So notice, since both of those divided by x, they have the same domain. And cotangent and cosecant both divide by y, so notice they have the same domain. And the range of this is similar to the one you get for the cosecant. It's that your y's have to either be less than or equal to -1, or they have to be greater than or equal to +1. Okay, so now we want to determine the period of a trigonometric function. From section 7.4, we saw that cosine of 420 degrees was cosine of 60 degrees, and that was still equal to 1/2. It says use your own words or a diagram to explain why this is true. Well, remember what we did here? So we're not going to really write out a sentence, but we took this and we said, because of coterminal angles, which means that the angle starts and ends at the same place no matter how many times it goes around, 420 minus 360 was 60 degrees. And then once you're between 0 and 360, you could figure out the angle where it's located in the quadrants, and we could find the ratio there. So what this means is that periods, if you know the period, and the reason we use 360 is because cosine and sine both repeat themselves every 360 degrees. Now, because there are domain restrictions for some of the other functions, their periods are going to be a little bit different. So let's just say this, that sine of theta plus 360k, where k stands for multiple rotations, either positive or negative. These are integers. So like this could be -1, which means you would subtract 360. Or it could be +5, which means you had to add, you already had a negative angle and you had to add 365 times to get it back to being between 0 and 360. So that's what that k stands for. That's also equal to 2 pi k, because 2 pi and 360 are the same thing. They're just in different measurements for radians versus degrees. And that actually equals sine of theta. Cosine's the same. Cosine and sine both take 2 pi to complete their period. So this would be 2 pi again, and this would be just cosine of theta. Functions that exhibit this kind of behavior where you can add or subtract something to the angle measure and the values of the sine and cosine function remain unchanged. In other words, it's the same, sine of 420 was the same as sine of 60. Those are called periodic functions. And in general, they're defined as the following definition. A function f is called periodic if there is a positive number p such that whenever theta is in the domain of f, so is theta plus p. For example, the function value of theta plus p is the same thing as the function value of theta. What that means is they have the same height. So notice, if I wanted to draw a line, I'm going to take away this secant function right here. If I wanted to draw the line y equals 1, notice that there are multiple values and they go in 2 pi groups pretty much, because this goes from negative 2 pi to 0 and 0 to 2 pi. Notice that every time we hit that same height on our function, because that's what f of a number is, it's the height, it's the y value, that has happened every 2 pi. So that's kind of interesting. So that's kind of what they're referencing here. The period of sine is 2 pi, so we already determined that. Oh, I lost my ability to use my pen. So 2 pi, we already know that the period of cosine is 2 pi. The period of the tangent function, so let's look, I can type this into Desmos, even though we haven't formally learned how to graph these yet. And you'll see that tangent, it has a little bit different going on here. So like if I want to know when does tangent have y equals 1, so I'm just making up a height. Notice that this happened here at pi over 4 and it happens again at 5 pi over 4. If you subtracted those two values from each other, you could see how much time it took for this to repeat its pattern. 5 pi over 4 minus pi over 4 is 4 pi over 4. That is just pi. So tangent repeats not every 2 pi, but every pi. So that means that's its period. And since cosecant function comes from the sine function, it has the same period. Similarly, the secant function and cosine function have the same period, and the cotangent and tangent function have the same period. So that means that when we look at cosecant, it's related to sine, so it's going to have the 2 pi. Secant is related to cosine, so it will also have 2 pi, and cotangent is related to tangent, so it will repeat its values of y for every pi. So then how can we use this? Well, hopefully we can use it to find exact values. So find the sine of the exact value here and the tangent of this exact value. So sine of 390 would be, let's subtract 360 from that. So we're kind of thinking of this as plus 360 times negative 1, essentially. So this equals sine of 30 degrees. And sine of 30 degrees, remember, if you don't remember from our previous notes, you can always think of the picture. Those special triangles, this is a 30, 60, 90. Across from 30, remember, is always 1. Across from 90 is double that. 60 is the square root of 3. And we're in quad 1 here, so everything is positive. And then remember that is opposite over hypotenuse, so it's 1/2. You will need to get to a point where you have those memorized. I just don't like to jump right into that with students. So you can always go back to drawing the triangle if you need to. And then 19 pi over 4, we would need to subtract 2 pi from this. So we need to get a common denominator. Multiply this by 4 over 4. That would be 8 pi over 4. And notice that comes out to 11 pi over 4, which means we didn't quite get rid of enough. So I'm going to subtract another 8 pi over 4 since that's still 2 pi. So that would be 3 pi over 4. If you remember, so we're doing tangent of 3 pi over 4. So remember, 3 pi over 4, you can count your 4s by the quadrants. This is 1 pi over 4. 2 pi over 4 is pi over 2. And 3 pi over 4 is here because 4 pi over 4 is pi. So remember, it takes 4 of those to get across to pi when you're talking about dividing it in fourths. So 3 pi over 4 is over here. And remember that anytime it's a divide by 4, that's a 45, 45, 90 triangle, which means these are both 1s and this is a square root of 2. And in this quadrant, the x's are negatives, but the y's are positive. So remember, tangent is opposite over adjacent, so that's 1 over negative 1, which is negative 1. So if you can convert these down to their correct measurement between 0 and 360 or 0 and 2 pi, then you can find the quadrant and location of them, especially for these special triangles where we already know the triangle breakdown. If your triangle is not related, if you have a, sine of 32 degrees, we have to use our calculator for that because we don't have special triangles that help us memorize those. Okay, and then this is the last page for this section, using even odd properties. This says recall from earlier chapters. If you haven't taken 136, which hopefully everyone has, that's what they're referencing. They're referencing that functions are even when they look like this. In other words, they have y-axis symmetry. This is an even function. And a function is odd if it has origin symmetry, which means if you have x and y on a point, then negative x and negative y also has to be on that same graph. You change both signs and the point still has to be there. So this is origin symmetry, which is related to being odd. So f is even if, the way I always remember this was, look at your y values. Your x was positive here, your x was negative here, but they had the same height. So that means f of x is the same thing as f of negative x, because f of means the height after this is the output. So the height is the same regardless of if the x inside was negative or positive. Odd is a little different. If you plug in a negative x, see right here, so this would be negative x, you actually get the opposite of the original. So that's how they write that. They say the x changes signs and so does the whole thing, the y value. So to consider this, we need to think about plugging in something we know and checking the negative of it to see if it actually comes out to have the same y or opposite sign y's. So if we do, sine of 30 degrees, which we know to be 1/2, then we try to do sine of negative 30 degrees. Well, negative 30 degrees is down here, and notice sine is related to y, remember, y over r, which is 1 for us. So whatever this point value is here. So notice down here the y is negative. So sine is going to be negative in this quadrant down here, which means that when you plug in a negative, you get a negative y. And when you plug in a positive x, you got a positive y. So that means that it is a odd function because it has the origin symmetry. For cosine, we would do cosine of 30 degrees, which is square root of 3 over 2, and cosine of negative 30 degrees. Well, notice in quadrant, that's down here because you're going negative 30 degrees instead of positive. X's have stayed exactly the same, and cosine is related to x. So notice this would still be square root of 3 over 2. So that means that this function is even. So the cosine function is even, the sine function is odd. The others are, the box got messed up. The others are going to work as follows. So, it does not want to agree with me right now. Sorry, this is a glitchy system. The sine is, like we said, odd. Cosine is even. Tangent is also going to be odd. And that's because tangent is a ratio of y over x, so the y does affect it. And then the reciprocals are exactly the same as their original. So notice that sine, cosecant, tangent, and cotangent are all odd functions, and cosine and secant are even functions. So the way we can think about this is that if cosine, and another thing to write here, so sine of negative theta, because it's odd, means that this is negative sine of theta. I'm going to write this in. Cosecant of negative theta would be negative cosecant of theta. Even means it stays the same, so cosine of negative theta would be the same thing as cosine of theta. Secant would be secant of theta. Tangent and cotangent, because they're odd, they're going to both have the negative on the outside of the original. So these are just quick ways to get the right answer. So since cosine's even, we know that this is identical to just cosine of 60 degrees. And remember, 60 degrees is up here. And that makes this a 30, 60, 90. So this is 1 square root of 3 and a 2. So cosine is adjacent over hypotenuse, so this is 1/2. Sine of negative 390. You probably still want to add 360 to this and make it something that is a little bit easier to deal with. So sine of negative 30 degrees. Since sine is odd, that means this is the same thing as negative sine of 30 degrees. Sine of 30 degrees is 1/2, and the negative out front makes that negative 1/2. Tangent is odd, but we also want to get this between 0 and 2 pi. So we need to add multiples of 2 pi until this gets into a format that we can deal with. And I'm probably going to have to think about this a little bit because it looks like we need to get pretty close to 37, and the closest thing I can think of that you can multiply by to get close to 37 would be 36. So let's just think, if this was 2 pi over 4, we turn 2 pi over 1. We multiply that by 4 over 4. Just trying to get my brain to get this the fastest way I can. So if we get a common denominator, we're trying to add multiples of 8 pi over 4. The closest 8 can get to negative 37 would be 32. So we would need to add this 4 times, and that would give us something in the negative range that we can still deal with. So I'm going to do times 4 of those. So negative 37 pi over 4 plus, this just means that I'm adding 8 pi over 4 times. So that would be 32 pi over 4, and that gives me negative 5 pi over 4. Okay. If you wanted, you could add another 8 pi over 4, and you could be at 3 pi over 4. I was kind of not going for that because I was trying to show you the rule. So if we stay at the negative version, that means that because this is odd, this would be negative tangent of 5 pi over 4. 5 pi over 4 is in quadrant 3. There's never enough room on these notes. Quadrant 3 is down here. So that is, remember, 45, 45, 90 triangle, negative 1 x, negative 1 y, and square root of 2, because this is negative x's and negative y's. So that would be negative 1 over negative 1, which is positive 1, but we know that it's negative because of the negative out front there. So this is negative 1. And notice that, there's a couple different ways I could have done this. If I didn't want to use the even-odd relationship, I would have just kept adding until I got to 3 pi over 4, and then I would notice that if I did the triangle as 3 pi over 4, up here you do get that the tangent equals negative 1. So, and that's because the x's and y's would have different signs. So either way would have given me the negative 1 that I was looking for. And that is the end of the 7.5 notes.